Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video on eigenvalues and eigenvectors. So I once had a maths professor who said that along with solving systems of linear equations, calculating eigenvalues and eigenvectors is the most important thing you learn in linear algebra. So to give you an example of where it's used, this is used in Google's PageRank algorithm. That's the algorithm Google uses to show you which is the best result when you search for something. But we're not quite at that level there. Let's start at the basics. So what's motivating us here with eigenvalues and eigenvectors? Let's look at our Cartesian plane in R2. So you'll be used to seeing vectors in R2 like this, and we've also looked at applying to vectors linear transformations. Remember, that's when you multiply a matrix by a vector and it maps it to another vector, say over here. So the effect of the linear transformation could be to rotate the vector, dilate it, rotate it, whatever. So when we're looking at eigenvalues and eigenvectors, we're motivated by this fact. If you take any matrix for a linear transformation, there's a subset of vectors for which this linear transformation only stretches them. What that will look like, it'll take this black vector and move it to a vector like this. It's only stretched it by some scale factor. I should also point out it could stretch and reflect it, but it's taken a vector here, the black one, to another vector in the span of the original vector. In other words, what is happening is when we multiply the matrix by a vector, we get a scalar multiple of that vector. So let's set up an equation to show this. So what we have is a matrix times a vector equals a scalar multiple of that vector. So here, lambda is just a scalar, a real number called the eigenvalue, and x is the vector we're looking at, is the eigenvector. But x is defined to be a non-zero vector. And it's important that we make that distinction because otherwise literally any number would be an eigenvalue because a times the zero vector gives the zero vector all the time. Okay, so how do we go about solving this equation? Well, remember, when I multiply by I, the identity matrix, it doesn't change what I started with. So I can put an ix in here because x and ix are the same. So I can subtract the right-hand side from both sides of the equation to get this. Now I get 0 on the right-hand side, but it's actually the zero vector. So now what I can do on the left-hand side is factor out x. So x has to go at the end of the brackets. Remember that matrix multiplication is not commutative. I can't put it at the start of the brackets because if I expanded, I would get x times a, which can't be done. All right. So what we notice here is we have a matrix times by a vector is equal to the zero vector. We've actually come across this situation before when we looked at linear transformations. Remember the set of all vectors that you can multiply the matrix by to get 0, that is the null space or kernel of the matrix. But hang on a minute, we want x to be non-zero. So remember, a matrix has a non-zero vector in its kernel if and only if the columns of A are linearly dependent. They are not linearly independent. So for us to solve this equation, we need this matrix here to have columns that are linearly dependent. But wait a minute, when we looked at determinants, we discovered that a matrix has linearly dependent columns when and only when its determinant is equal to 0. So there will be a non-zero vector x satisfying this equation when and only when the determinant of A minus lambda I is equal to 0. This time 0 is just a number, not a vector. So this is what we solve. And it turns out that this will leave us with a polynomial called the characteristic polynomial of the matrix. So let's look at how we might actually solve this. Let's look at this matrix here. I want to find all its eigenvalues and eigenvectors. So to find the eigenvalues lambda, I solve the equation determinant of A minus lambda I is equal to 0. So I'm solving for lambda. So of course, you know that I, the identity matrix, just has 1s on the leading diagonals. So if I times this by lambda, I just times each element by lambda, right? So when I calculate A minus lambda I, all I'm doing is subtracting lambda from each of the elements on the leading diagonal, and I leave the off diagonal elements alone. So this is A minus lambda I. So I want to find the values of lambda that make A minus lambda I, this matrix here, have a determinant of 0. But I know that the determinant of this matrix is AD minus BC. It's the two elements on the leading diagonal multiplied together minus the two elements off the diagonal multiplied together. So I want that to equal 0. So let's just rearrange this equation, and then we'll collect like terms. Now to solve this, I could use the quadratic formula, but it's probably easiest to factorize. Two numbers that multiply to -5 and add to -4. And then to solve it using the null factor law, I get lambda equals 5 or -1. So they are the two eigenvalues of this matrix, 5 and -1. So this is the characteristic polynomial of the matrix. So if you have a 2 by 2 matrix, the characteristic polynomial is always degree 2. If you have an n by n matrix, the characteristic polynomial is of degree n. So you will always have at least one eigenvalue, but you'll never have more eigenvalues than the number of rows or columns in the matrix. Okay, so we found our two eigenvalues. Now we need to find the eigenvectors. So let's start by finding the eigenvector associated with lambda equals 5. So this is A minus lambda I, where lambda is 5, and I want to find a vector that I can multiply by this to get the 0 vector. So I'm solving the equation A minus 5I multiplied by a vector, I'll just call it x1, x2, gives me the 0 vector. So because the determinant of this matrix is 0, I know there will be a non-zero solution here. But I know that there are going to be infinitely many non-zero solutions, right? Because if a vector is in the kernel of this matrix, then any scalar multiple of that vector will also be in the kernel. So I'm just going to find a basis for the solutions. So how do I solve this? Row reduction. So this is my augmented matrix now, and I perform the usual row operations on it to get this form. So as I said, there will be infinitely many solutions because of this row of zeros. So we have x1 minus a half x2 is equal to 0, which of course means x1 is equal to a half x2. So any vector where the first one here, first entry, is half of the second entry, that will be in the kernel of this matrix, meaning it will be an eigenvector of this matrix. So if we take, for example, x1 equals 1, then x2 would be 2. this here is an eigenvector of the original matrix, and any scalar multiple of it will also be an eigenvector. So that is the eigenvector corresponding to the eigenvalue lambda equals 5. So please pause and copy this down if you need, because I'm going to rub this out and now find the eigenvector corresponding to lambda equals -1. So now we look at the case where lambda is equal to -1. So a minus lambda I becomes a plus I. So now we're just adding 1 to each element on the leading diagonal. So this is our matrix A plus I. So again, I want to find a vector I can multiply by this matrix to get the 0 vector. Again, there will be infinitely many such vectors. So I'm going to set up my augmented matrix and then perform on it the usual row operations. So again, there will be infinitely many solutions because of the row of zeros, and I have here that x1 plus x2 is equal to 0, which means x1 equals the negative of x2. Okay, so I have a vector, and any vector will do as long as the first entry is the negative of the second entry. So I could have the vector here 1 minus 1. So that vector will be an eigenvector, because if I multiply this matrix by the vector, I get the 0 matrix. So that means it will be an eigenvector of the original matrix. So this is the eigenvector corresponding to the eigenvalue lambda equals -1. And again, any scalar multiple of this vector will also be an eigenvector of the matrix A. All right, let's look at an example of a 3 by 3 matrix. So let's look at this matrix here, and we will calculate its eigenvalues. So first thing we do is subtract lambda I from it. So remember, that means that I just subtract lambda from each element on the leading diagonal, and I leave all of the other elements alone. So now I have to calculate the determinant of this matrix. So remember, I do this by cofactor expansion. So I take the first element and multiply it by the determinant of this matrix here. Next, I take the second element in the row and I multiply by the determinant of the matrix formed by these 4 elements. Remember, I have to stick a minus in front of the 2, because every second term when you're using cofactor expansion is a negative. And then finally, I look at the third term and I multiply that by the determinant of this matrix here. So of course, now I have a polynomial and I want to solve when that is equal to 0. So I'm going to need to make this a lot easier to work with by expanding all the brackets. So after I do that and I collect all the like terms, I'm left with this polynomial here. So I want to solve where this polynomial is equal to 0. So I want to solve minus lambda cubed minus lambda squared plus 6 lambda equals 0. So to make this easy, I'm going to multiply each side by -1, and I end up with something like this. So to solve for lambda, I can factor out lambda because it's in each term. And then what will be inside the brackets is a quadratic that I can further factorize. So of course I have either lambda equals 0 or this thing in the brackets equals 0. And if that thing in the brackets equals 0, then lambda is equal to 2 or -3. So they're the 3 eigenvalues, 0, 2, or -3. So again, I find the associated eigenvectors using row reduction. So I'm just going to show you one of the eigenvectors, just so this video doesn't go on forever, but the way you do the other two is the same. So I'm going to get rid of my working out for the characteristic polynomial, so please pause and copy this down if you need. So I'm going to find the eigenvector associated with lambda equals 0. So of course, if lambda equals 0, then A minus lambda I is just the original matrix. Okay, and that's because this original matrix already had determinant of 0. So we didn't actually need to subtract anything from it for it to have determinant 0. So I want to find a non-zero vector x1, x2, x3 such that when I multiply the matrix by it, I get the 0 vector. So this is my augmented matrix, and I perform the usual row operations on it. So if I keep going until it's in row reduced echelon form, I get something that looks like this. So once again, I have a row of zeros at the bottom, which tells me that there are infinitely many solutions, and this variable here, x3, is a free variable. So I'm going to write the solution in terms of x3. So that's the solution in terms of x3, so we can write this as a vector. So x3 times 9 over 7, you get x1, times negative 15 over 7, you get x2, and times 1, you get x3. So this here is the eigenvector. We can times everything by 7 if we like, so that all the elements in the vector are integers. So this is our eigenvector with integer entries, and of course any scalar multiple of that will also be an eigenvector. So let's just quickly check we've got the right vector. If we multiply our original matrix by this vector, we'll get a 3 by 1 vector, so let's check. So first entry will be 9 minus 30 plus 21, which is 0. The next one will be minus 9 plus 30 minus 21, again 0. And the third entry will be 45 minus 45, which is 0. So if we multiply this matrix by our eigenvector, we get the 0 vector, which is of course 0 times the original matrix. Okay, so that's shows us that we're right, that this is an eigenvector. All right, we're just going to very quickly look at the case now of triangular matrices. So it turns out that if you have a triangular matrix, its eigenvalues are just the entries on its leading diagonal. So remember also that a diagonal matrix is a type of triangular matrix. It's a matrix that's both upper and lower triangular, so it also follows this rule. So rather than go through and calculate all the eigenvalues here, I just want to look at why this rule is the case. So let's look at the matrix on your screen. Let's first look at the 1, 1 element here. So that's really simple. If I subtract 1 from each element on the leading diagonal, this entry will become 0, and I will have a row of all zeros. And that, of course, will mean that the determinant of the whole matrix will be 0. Look next at this element here, 4. If I subtract 4 from each element of the leading diagonal, the first row is this, and the second row will become this. So you can see the second row will become a scalar multiple of the first row. That means there will be at least one column that is a scalar multiple of another column, and then the determinant of the matrix will be 0. So let's look now at the 3 element 9. So if I subtract 9 from each element of the leading diagonal, the third column will become this, and the fourth column will become this. So you can see the fourth column is just a scalar multiple of the third column. So again, linearly dependent column or row means the determinant of the matrix will be 0. And finally, the 4, 4 element. So if I subtract 6 from each element on the leading diagonal, then I will have a column of all zeros. So the idea here is that the values that are on the leading diagonal of a triangular matrix, if you subtract them so that you make any of the entries on the leading diagonal 0, you will end up with a column or row that is a scalar multiple of another column or row. And that includes the case where you have either a row of all zeros or a column of all zeros. In either case, having a row or column that is a scalar multiple of another means that the determinant of the matrix will be 0. So if you make any of these elements on the leading diagonal 0, then the determinant of the matrix will be 0. All right, I know this is a very important and very long video. Sorry that it was so long. This has been the luckiest maths teacher in the world. Have a great day.